The space tug delivers a package to low Earth orbit, a manipulator robot, a package of truss components, a bundle of rail sections, a solar array, and a stack of docking discs. The robot assembles the truss section by section. It attaches the track sections and the docking discs to the truss as it moves along the track. Finishing the working station, you have to add the solar array, the crew habitation units, the attitude control system. You want to fill your propellant depots with fuel. You'd have temporary storage containers for large cargo. You'd have liquid and electric plasma and ion space tugs. The docking truss is then ready to use. If you could do the first one at low Earth orbit, which is a transfer point primarily, then the process is then repeated at L1, which is a much larger truss and a much larger station. And you can also use electric tugs to get stuff out there, such as liquid fuels. If your liquid fuels in a depot, you can put that onto an electric rocket system and move it very slowly out to L1 and save the huge mass of propellant that would be required to get it out there. So that's what this would look like. It's here, as you can see, where they've accumulated more of the vehicles. Here are all the stuff from Mars. It's got the solar array on it. You can see some of the unoccupied vehicles. On the back of the truss, opposite the rail, would be more of these propulsion units, which don't need the robot to do anything to them. If they need to get fuel, they can move themselves over to one of the depots, dock with it, and take on fuel. This is a close-up, so you can see the arrangement of they're like, almost like you can imagine them as soda cans with 6 cans arranged in a circle around one can. So you can fill those other cans with water, food, equipment, and even asteroid rock to serve as shielding mass to protect the crew from heavy nuclei and solar protons. And you can see a couple of the Mars ferries docked there on the top of the truss, and a couple of the docking discs with the latching mechanism in the center. Remember, that's a 15-meter truss. The discs are 8 meters across, and the latches are 2 meters across. There's a view looking straight down on it. And there, right on the bottom left, is a crew ferry. See the crew capsule on the ferry? It has a much nearer point than the cargo ferry. So now we get into the part that's about Mars. This is how you enable us to send a fleet of vehicles to Mars, not a gargantuan Battlestar Galactica type vehicle which can tear itself apart when it leaves. What time do I got now? So I just keep track of it here.
It's 3:30.
Okay, we're doing good.
Yeah.
Okay, so we've gone through the critical part of the show, which is all new information. Now, on the NSS website, under it's nss.org, settlement, Mars, access to Mars, you can see the 2-year-old version of the show from here on, which is primarily about what you do when you get to Mars. So the big issue is here, you don't want a flags and footprints vehicle or architecture, because if you do that, then you're going to have another post-Apollo interregnum, which could last 20 or 30 years when nothing will be going on if the government has anything to say about it. So I'm not really expecting the government to do very much, but the basic issue, even if you're a private company, if you're going to be serious about it, you really need to have reusable vehicles. So the rationale for a robust mission: larger crew for safety and a wider set of skills, redundancy of vehicles and equipment. It creates and maintains a permanent orbital and surface-based system where the first expedition, more actual science and exploration is accomplished. It increases the ability to use significantly more types of local resources on Mars for base support and fuel. So this talks about the business about having a single large vehicle versus a fleet. And if you have a single large vehicle like a space station, you're going to have to waste an awful lot of mass so the vehicle doesn't tear itself apart when it leaves Earth. So instead you have a Mars fleet. Each vehicle takes itself to Mars. the ferries take themselves. They fuel up at the depots and they go off to Mars with probably one piece of cargo already preloaded in their cargo bay. The propellant depots and the cargo racks and the crew vehicles have to have a propulsion unit, a transit vehicle, attached to them to push them to Mars. They also have to have a large aero shell or aero shield for aero braking. This allows an expedition massing thousands of tons, which is able to land much more cargo on Mars. The amount of fuel needed for departure from L1 to Mars varies depending on the year by almost a factor of 3. So the year you leave is very important if you're trying to deliver a large amount of cargo to the surface. So this goes through the rationale of why you have a certain minimum mass for your first set of ferries. The critical thing is you have to have enough mass landed to build your fuel production facility, because no ferry can take off from Mars again until you have fuel on Mars. It's very difficult to bring fuel down to take off again. You'd have to have multiple vehicles, and not all those vehicles would be expendable vehicles. So the critical thing is making fuel on Mars, and so I've simply said that I think 175 tons, which represents 7 cargo ferries trips down to the surface, is fine. Then later on, with multiple trips down with the same ferries, the total landed cargo capacity of this expedition, not including the ferries, is 625 tons. Now, almost everybody else has less than 100 tons. So this is a serious expedition, able to do a lot of work. And this is another issue here. You've got the 2 redundant 200-ton propellant depots, the 2 large cargo carriers, the 3 shielded crew habitat clusters. One you would use and leave in low Mars orbit, and the other 2 could be used for the crew to go back to Earth, again for redundancy. If something happened to one vehicle, you'd have another vehicle and the crew would transfer to the other vehicle to get back to Earth. And so the total mass and fuel taken to Mars is about 3,000 tons. It's about 6 times heavier than the space station. This talks about how you build it up. We've already kind of discussed that. Tells all about the different stages of getting it up there. So you accumulate a fleet at L1. This allows like 1 vehicle to leave per day during a narrow Mars launch window. Now, the Mars ferries and transit vehicles in the fleet launch themselves from L1 to low Mars orbit, reaching it by aero capture. So all they need is a heat shield to do an aero capture, and the ferries already have their own heat shield, and the other ones have an external heat shield or aero shell, which they would be put aside for future use once you're in low Mars orbit. Now there's the Mars expedition all ready to leave for Mars. This is at L1. So the Mars fleet then departs from Mars individually. About 1 to 2 vehicles can depart per day, roughly 1 to 3 kilometers per second velocity change. A good year needs about 600 tons of propellant, a bad year about 1,700 tons. Payload to Mars includes 400 tons of fuel, which is the cargo or payload not used to leave to go to Mars. Okay, using aero capture at Mars, it uses a very large diameter aero shield or integral aero shell to slow yourself down by flying through the atmosphere 1 time. Let me just go ahead so you can see how that looks like. So here you're coming in at the at the top of the frame at like probably 6 or 7 kilometers per second. You go through the atmosphere, maybe 40 to 60 miles high. You slow down until you're going about 4 kilometers per second. You then go back up slightly till you're about 400 kilometers above Mars, at which point you give a small burn of about 100 meters per second to circularize your orbit so you don't pass through the atmosphere a second time. You don't want to do that because most of the vehicles aren't intended to land immediately. And then you're in low Mars orbit. This would be a near equatorial orbit to take advantage of the 240 meters per second eastward rotation of Mars. There's a picture of a vehicle coming in with, you can see how the stuff behind the aero shell is protected by the shell itself. And the shell itself can then be detached if you're just going to stay in orbit and put to one side for later use. Here's a ferry coming into Mars, low Mars orbit using aero capture. It has its own built-in heat shield because it has to enter the Mars atmosphere anyways, which is much more stressful. So this talks about the best place for a Mars orbit base location. So you want a circular orbit about 400 miles high so it doesn't have a lot of drag. It gives you a lot of, it makes it easier to land and take off because Mars is rotating to the east by 240 meters per second. That's about 6% of takeoff energy and about 25% of landing energy that's required. And this goes through the rationale for designing the way station. It goes through a lot of details.